Welcome to the deep dive. You sent over some really fascinating material on algebraic number theory, and one name just kept coming up, Richard Dedekind.
Mm-hmm.
It seems like when mathematicians first started exploring these, well, numbers beyond our regular integers.
The algebraic integers, yeah.
Right, the ones that pop up as roots of polynomial equations,
Yeah.
the ones with integer coefficients. There was this initial hope, wasn't there? Almost an assumption.
Oh, absolutely. A very natural one. We're so used to the fundamental theorem of arithmetic for our everyday integers.
That every number breaks down uniquely into primes. 12 is 2 times 2 times 3, and that's it.
Exactly.
Yeah.
It's such a cornerstone, such a, fundamental part of how we think about numbers. It just seemed logical that this neat property would carry over into these new extended number systems.
But the material you shared suggests things started to get a bit complicated.
That's putting it mildly, yeah.
Especially with the work of Ernst Kummer. He looked at certain systems, right?
Mm-hmm.
Related to roots of unity.
That's right. And he found something quite, shocking.
For you and me, that idea of unique breakdown is just so basic. What exactly went wrong there?
The core issue was the failure of unique factorization. Simple as that, but profound. In some of these algebraic number systems, a number you could factor into what seemed like the equivalent of primes. Let's call them indecomposable elements for now.
Right. The building blocks.
Yeah. That number could actually be factored in multiple, completely distinct ways.
Wait, multiple ways?
Yeah.
Using different sets of these indecomposable bits.
Entirely different sets, yes. Imagine, like you said, if 12 could be 2 by 2 by 3 1 minute, and then, 5 by 7 the next, using different primes. It completely undermines any attempt at consistent arithmetic.
That sounds chaotic. And it wasn't just a lack of uniqueness, was it? I think I read something about these indecomposable things not even acting like proper primes.
Exactly right. That's the other crucial part. You know how a prime number, if it divides a product, say P divides AB, then P must divide A or P must divide B.
Yeah, that's fundamental.
Well, in these systems Kummer studied, these indecomposable elements could divide a product without dividing any of the individual factors.
Oh, wow. So the basic prime test failed too.
It did. It was a fundamental breakdown of the prime-like behavior we really depend on.
So for anyone trying to build a solid theory for these algebraic numbers, this must have felt like, like the ground was shifting under them.
It was a serious obstacle, a huge challenge. How do you build a theory of divisibility when your basic components don't follow the rules you expect?
It threatened the whole enterprise, didn't it?
Yeah.
You couldn't just extend the tools from basic number theory if unique factorization wasn't guaranteed.
Precisely. Many standard techniques just fall apart without it.
Which leads us, I guess, to the main point of this deep dive. Based on your sources, how did they fix this? How did mathematicians, rescue the situation and restore some kind of fundamental theory of divisibility?
Right.
And the name that comes up again, the one who had the really groundbreaking idea, is Dedekind, with his concept of ideals.
Exactly. Dedekind was really driven by this need for a general theory, something that worked without exceptions for all algebraic integers. He knew Kummer's work, saw the problems.
And he wanted a universal fix.
Yes. He built on his own earlier research, of course, but Kummer's observations were a huge motivator. He understood how critical a reliable theory of divisibility was.
It's interesting, though, that one source mentioned he didn't jump straight to ideals. He tried something else first, something about higher-order congruences.
He did, yes. That was his initial line of attack, and it wasn't fruitless. It actually worked quite well in many specific situations, gave partial answers.
But not the complete picture.
Not quite. It didn't provide that comprehensive, universally applicable framework he was really aiming for. There were still gaps, systems where it didn't fully tidy things up to his satisfaction.
So he hit a wall with that approach, essentially, and needed a new angle.
He did. He realized the limitations and shifted his focus, moved away from those, let's say, more formal computational methods.
And towards something more fundamental.
Towards the core concept of divisibility itself. What does it mean for one number to divide another in these systems?
What was the key shift in his thinking then?
The big change was deciding not to define these hypothetical ideal numbers, that Kummer had sort of hinted at these missing factors.
Ah, okay, so Kummer thought maybe there were hidden numbers making the factorization unique.
In a sense, yes. But Dedekind thought, let's not invent new numbers. Let's focus on the relationships, specifically the divisibility relationships between the algebraic integers we already have in our number field.
Okay, that does sound more grounded. Look at what's actually there, not what might be missing.
Yeah.
And that led him to ideals. So what is an ideal? For someone like me, it still sounds a bit Abstract.
Okay, think of it like this. An ideal isn't a single number. It's a special kind of set or collection of algebraic integers all living inside the same number field.
A set. Okay.
Yeah.
What makes it special?
The numbers in the set all share a particular divisibility property. Dedekind's own definition put it something like this. An ideal, let's call it A, is the collection of all the numbers in our domain that are divisible by some underlying, perhaps not explicitly defined, ideal number.
So the set consists of all the multiples of some maybe hidden divisor. It's like focusing on the effect of division rather than the divisor itself.
That's a great way to think about it, exactly. Dedekind was actually a bit wary of treating Kummer's ideal numbers too much like regular numbers.
Why was that?
He worried it could lead to flawed logic, maybe contradictions down the line if you weren't careful. His goal was rigorous. Define ideals and define how to multiply them, using only the properties of the algebraic integers we already know exist in the system. No fuzzy ideal numbers needed in the definition itself.
Right. Keep it self-contained within the known structure. Okay. Yeah. So these ideals are sets with shared divisibility. Do they have specific defining properties? Can any old set be an ideal?
No, definitely not. Dedekind found very precise characteristics. Let's start with the simplest type, maybe. Principal ideal.
Okay.
Take any single algebraic integer, call it alpha. The principal ideal generated by O is just the set of all its multiples, everything you get, by multiplying A by any other algebraic integer in that same domain.
Got it. So like with regular integers, the principal ideal for 5 would be means 10, 5, 0, 5, 10, all the multiples of 5.
Exactly that. It's a very direct analogy.
And you mentioned something about units, that the ideal stays the same if you multiply the generator out by a unit. What's a unit again in this context?
Good question. A unit is an algebraic integer that basically acts like 1 or McCasted 1 does for regular integers. It's an algebraic integer whose multiplicative inverse is also an algebraic integer within the same system.
So it divides everything.
Essentially, yes. It divides every other algebraic integer in the domain. Multiplying by a unit doesn't fundamentally change divisibility properties within that system. So the set of multiples, the principal ideal generated by O, is the same as the set generated by O times a unit.
Okay, that makes sense. Units are sort of structurally neutral for multiplication. So that's principal ideals.
Yeah.
But you said Dedekind's idea was more general. What properties define any ideal principal or not?
He nailed it down to 2 fundamental closure properties. First, take any 2 numbers inside an ideal. Their sum is also in the ideal, and their difference is also in the ideal. It's closed under addition and subtraction.
Okay, property 1. Closed under addition and subtraction.
Second, take any number inside the ideal. Now multiply it by any algebraic integer from the entire domain, not necessarily one inside the ideal, just any number from the system we're working in. The result, that product, must also land back inside the ideal.
So it absorbs multiplication from the outside. It's closed under multiplication by any element of the whole ring of algebraic integers.
Precisely. Closure under internal addition-subtraction and closure under multiplication by elements from the entire ring.
Those 2 rules seem surprisingly simple, actually.
Elegant, right. And here's the absolute core of his theory, the breakthrough. Dedekind proved that any set of algebraic integers that satisfies just those 2 properties is an ideal.
Any set.
Any set behaving that way. It automatically corresponds either to a principal ideal generated by a single existing number, or it corresponds precisely to one of those necessary ideal divisors that Kummer had sensed were missing.
Wow. So he defined ideals by their behavior, by these intrinsic properties, rather than needing to point to a specific ideal number generator.
Exactly. It sidestepped the whole problem of defining those potentially problematic ideal numbers directly. The definition is based entirely on the existing numbers and their operations.
That's a really clever shift in perspective. Okay, so we have ideals defined by these 2 closure rules. How does this get us back to sorting out division? How do we talk about one ideal dividing another?
Dedekind defined ideal divisibility very naturally using the set idea. We say an ideal A is divisible by an ideal B if every number inside ideal A is also inside ideal B.
Oh, so it's just set containment. If A is a subset of B, then B divides A.
That's it. Simple, clean. If A, B, then B, A. Or you could say A is a multiple of B and B is a divisor of A. It lines up perfectly with how we think about multiples, like the ideal 6 is contained in the ideal 2.
Okay, that makes intuitive sense. Containment means divisibility. What about prime numbers? How does that concept translate? What's a prime ideal?
A prime ideal P is an ideal that isn't the whole ring of integers itself. That's like the trivial divisor 1.
Right.
And its only ideal divisors in this containment sense, are itself and the whole ring.
So just like a prime number only has 1 and itself as factors, a prime ideal only has the whole ring, like 1 in itself, as ideal divisors. It's minimally divisible in a way.
Exactly. It's analogous. It's minimal in terms of the ideals that contain it, apart from the whole ring.
Okay, ideals, ideal division, prime ideals. Now the big one, multiplication. That was key to unique factorization for numbers. How do you multiply these sets, these ideals?
Right. This needed careful definition, too. The product of two ideals, say A and B, written ab, isn't just the set of all products ab where A is in A and B is in B. That wouldn't necessarily satisfy the closure rules.
Ah, okay. So it's more complex.
Slightly. The product ideal ab is defined as the set you get by taking all possible products of an element from A and an element from B, and then considering all possible sums of those products.
So you multiply elements pairwise, and then you take all sums of those results to make sure you get closure under addition back.
Precisely. You need the sums to guarantee the result is closed under addition and subtraction, fulfilling the first ideal property. This definition ensures that the product ab is itself always an ideal.
Okay, that makes sense why the sums are needed. And does this multiplication behave as expected regarding division?
Yes. An immediate consequence of the definition is that the product ideal ab is always contained within ideal A and within ideal B. Meaning, by our definition of divisibility, ab is divisible by both A and B, just like how the number 6 is divisible by 2 and 3.
Okay, perfect. So the definitions seem consistent. We have all the pieces. Ideals, prime ideals, division, multiplication. Now, the payoff. How did Dedekind use this machinery to finally fix the unique factorization problem?
This is where it all comes together. Dedekind proved two absolutely fundamental theorems about these ideals.
Okay, theorem 1.
Theorem 1 basically establishes ideal division. It says, if an ideal C is divisible by an ideal A, meaning AC doesn't hold, remember AEB means BA, so if C is divisible by A, that means AC, then there exists one and only one unique ideal B, such that the product A equals C.
So if A contains C, you can always find a unique ideal B such that multiplying A by B gives you C, like canceling out the A.
Exactly. It brings back that deterministic nature of division. If it divides C in the ideal world, the quotient, which is another ideal B, is uniquely determined.
That sounds crucial. And the second theorem, this must be the big one for factorization.
This is the punchline. The second fundamental theorem, every ideal, except the trivial zero ideal, can be written as a product of prime ideals. And crucially, this representation is unique apart from the order of the factors.
There it is. Unique factorization restored.
But notice it's unique factorization of ideals into prime ideals, not necessarily unique factorization of the original algebraic integers into indecomposable integers.
Ah, right. So the problem Kummer found with numbers like, say, 6 in that range, z squared 5, having two factorizations, 2 by 3 and 1 plus squared 5, that still happens at the number level.
Yes, the numbers themselves might still factor in multiple ways into indecomposables.
But the ideals generated by those numbers, or related ideals, will factor uniquely into prime ideals.
Precisely. The ideal generated by 6 in that ring factors uniquely into a product of 4 distinct prime ideals. 2, 1 plus squared 5, 2, 3, 1 plus squared 5, 3, 1 squared 5. And the ideals generated by the factors on both sides, like 2 and 3 and 1 plus squared 5, they all break down uniquely into combinations of these same prime ideals. The uniqueness is restored at the ideal level.
It's really elegant. It shifts the primeness up a level of abstraction to these sets.
It is. Dedekind rigorously proved both theorems, laying a solid, complete foundation. It resolved Kummer's paradox and gave mathematicians a reliable way to handle divisibility in these complex algebraic number fields.
It sounds like a truly monumental piece of work.
Right.
What came next? What were some consequences of this theory of ideals?
Well, one hugely important concept that flows directly from this is the ideal class group.
Ideal classes, what are those?
It's a way to measure how far the ring of integers is from having unique factorization of numbers. Basically, you group ideals together. Two ideals are in the same class if one can be turned into the other by multiplying by a principal ideal. Or, maybe more intuitively, if they become principal after multiplying by the same third ideal.
Okay, so it measures the failure of ideals to be principal, generated by single numbers.
Exactly. In systems where all ideals are principal, there's only one class, the class of principal ideals, and you actually do have unique factorization of numbers. The number of distinct ideal classes tells you in a precise way how much unique factorization fails for the numbers themselves.
And is this number of classes predictable?
Amazingly, yes. Dedekind proved that for any given algebraic number field, the number of these ideal classes is always finite. This is a really deep result called the finiteness of the class number.
Always finite. That's surprising.
It is. It connects back to earlier work, like Dirichlit's work on classes of quadratic forms. But Dedekind's ideal theory provided a much more general viewpoint and proof. It links algebraic number theory to other deep areas of mathematics.
It really is fascinating how this abstract shift from numbers to sets defined by properties unlocked so much. It makes you think, doesn't it?
It does, and it fits Dedekind's whole mathematical philosophy, as we maybe touched on. He did something similar, defining real numbers with his cuts in the rational.
Right, defining new things purely based on phenomena within the system you already understand.
Exactly. Define irrationals using only rationals. Define ideal behavior using only the existing algebraic integers and their operations. Avoid introducing potentially ill-defined external objects if you can build it rigorously from within.
So just to recap then, we started with this hope that algebraic integers would factor nicely like regular ones. Kummer found that wasn't always true. Unique factorization could fail, and the prime-like elements didn't always act prime-like.
Right, a major crisis.
And Dedekind's brilliant solution was to step back, ignore the problematic factorization of individual numbers for a moment, and focus instead on these special sets called ideals, defined by those two closure properties.
Terrific summary. Sets closed under addition, subtraction, and under multiplication by any ring element.
And then he showed that these ideals, these sets, do have unique factorization into prime ideals. The fundamental theorem was saved, just operating at the level of ideals.
Beautifully put. It provided the robust foundation needed for modern algebraic number theory and much of abstract algebra that followed.
It really is remarkable. You know, thinking about this deep dive, it strikes me how powerful that shift in perspective can be, moving from focusing on individual items to focusing on collections defined by relationships or properties. I wonder where else that kind of thinking might unlock problems, maybe even outside of pure math.
That's a great question to ponder. It's a recurring theme in mathematics and science, finding the right level of abstraction or the right collective properties to focus on. What seems intractable at one level might become clear when viewed through the lens of sets, structures, or systems.
Definitely food for thought. Well, thank you so much for walking us through Dedekind's incredible insight today and shedding light on ideals.
My pleasure entirely. It's a truly beautiful piece of mathematical history. And for anyone whose interest is piqued, I'd absolutely encourage them to explore algebraic number theory further. There's a rich world there, building on Dedekind's legacy.